So here's some intro to kinetics, notes to get you started. The definition of kinetics in chemistry is the study of reaction rates. And if we want to contrast that to other things that we've already looked at, or something we've already looked at, is thermodynamics. So thermodynamics, with the help of delta G, right? If we have a negative delta G, that tells us that a reaction is spontaneous, that it will occur without ongoing outside intervention, but it tells us nothing about how fast that reaction will occur. So that's what kinetics takes a look at. And it's kind of, like I said, a bit of an odd duck. It's kind of quirky, but I think you'll really like it. So thermodynamics, kinetics are two of the three kind of really big deals in AP Chem. And then the last one, which we'll get to in a couple months, is equilibrium. And that talks about the extent to which a reaction occurs and forms its products. We'll talk about collision theory, which is that in order for a reaction to occur, not only do the reactant particles have to collide with one another, but they have to do so effectively. So in order for a reaction to occur, there have to be effective collisions. And there's two pieces of criteria for effective collisions. One is that you have to have collisions with sufficient energy. And then the second is that you have to have collisions with proper orientation. All right, and then there's a big and here. This is not an or situation. You must have both. Do leave some room because we're going to come back and just add an addendum there to sufficient energy, just a little more specific. So let's look at an example with HI, hydrogen iodide. If you have two hydrogen iodide molecules that are decomposing and turning into H2 and I2, not only do they have to hit with enough force or enough energy, but they also have to have proper orientation. So for example, if they collide in this way, that would not be set up to actually break these individual bonds and then form HH bonds and II bonds. Okay, the only way that that would actually happen is if they are colliding this way, right? So that would give proper orientation. As long as there was sufficient energy, you would have an effective collision there and you could get your products. We're going to look at a potential energy diagram, also known as a reaction energy profile. And the first thing we're going to do, as always, is look at our axes labels. Okay, so on the x-axis, you can actually have a few different labels. A common one is the progress of a reaction. So the R over here stands for reactants, the P over here stands for products. So the course of the reaction, progress of the reaction, that can be one label. For the x-axis, you can also have reaction coordinate. It means the same thing as progress of reaction. And then third, you might sometimes see this, but this is not my favorite, hence the frowny face, time. That's just a bit too quantitative for what this is showing. This is just saying you start with reactants, what happens potential energy-wise as you get them to products. And you can see it. You may have thought this. You may have thought, well, what do you mean what happens? It just goes reactants to products. It's a straight line. And you can see that's not, in fact, the case. There is a camel hump situation that we have to deal with. On our y-axis, you've seen, plenty of graphs like this before. The label is potential energy. So lots of vocabulary to denote here. You already know some of it, though. Okay, so if you're talking about your starting point for your reactants is higher in potential energy than your products, okay, this change right here is your delta H. Okay, that's your enthalpy change. So delta H, and in this case, if you do products minus reactants, final minus initial, you're going to get a negative value because your products are lower in potential energy. So this is showing an exothermic reaction. That's what this diagram is depicting. Okay, now we also need to talk about this hump. What is going on here? Okay, from your reactants up to this peak. That is something called activation energy. So E sub A. And E sub A stands for activation energy. So, for example, if you have a match is clearly or a lit match is very, very clearly exothermic, it's on fire, right? But you do have to put some energy into lighting that match, and then it will self-sustain and it will be a spontaneous exothermic reaction. Finally, we're getting to that little bit of intervention you have to put in at the start, and that's called activation energy. Okay, so if this hump was even higher, that means we have to put more energy in order to kind of get that reaction started, and then, it can continue on its own. We talked about spontaneous reactions occurring without ongoing outside intervention. So this is not an ongoing situation, but it's like a one-time intervention. As long as you can get to this activation energy, then you can get over that hump and your reactants can become products. So let's take a look at what's going on at this peak. First of all, please recognize at this peak, it is really high potential energy, way higher than even the potential energy of your reactants. So at energies this high, we have very unstable situations. Okay, so what you would have here, it actually goes by two different names, you need to know both, is a transition state, aka an activated complex. Activated complex. And as I said, it's a really high energy situation. So your activated complex or your transition state, it's really unstable, okay? We can't isolate this and put it in a jar in the prep room and then really study it. And what's happening in the transition state is that bonds are simultaneously breaking and forming at the same time. So let's draw in this other set of axes, let's draw an endothermic reaction profile that goes more slowly than the first one. Okay, so if you're going to set your reactants starting here, that means that your products would have to end at a higher potential energy because it's endothermic. So the change here, your delta H would be positive. Okay, doesn't really matter how much more positive. And then the fact that I said it's a slower reaction, that means that the hump, the activation energy, would have to be greater than the previous one. And that would mean that we have a slower reaction. So your activation energy starts at your reactants, ends at the hump. So we can see we have a much larger activation energy here than we do here. So this would react more slowly than this one. Why? Because it would take more energy to have those effective collisions that are needed in the case of the higher hump, of the greater activation energy. So here's what can lead to a transition state. If you have an effective collision between these two HI molecules, at the same time, you're going to get these bonds partially forming to make your H2 and your I2, and then you're also going to be breaking these bonds. And that's going to be really unstable. It's going to be high in energy. That's an example of what your activated complex would look like. So I'm sure you know about many of these already, but ways to increase the rate of reaction. Obviously doing the opposite of these would decrease the rate of the reaction, but you could stir, mix, shake to get more collisions to happen. You could increase the concentration of a reactant. However, that really only happens with aqueous or gaseous because if your units of concentration are in moles per liter, you can increase the number of moles of a solute per liter of solution, or you can compress a gas and get more moles in a liter, but you can't do that for solids and liquids. For solids and liquids, though, you can increase the rate by increasing the surface area. So what that means in the case of solids is you crush. Like if you have a sugar cube and you crush it up, the crushed up sugar should react faster. And then if you have a liquid, you could put it in a larger container. just so that there's more surface area exposed. And then you can increase the temperature or heat something, and then you can add a catalyst. So definition of a catalyst, it speeds up a reaction, which is why we're adding it, but it's not itself consumed, so it's not a reactant. So it remains generally unchanged even as the reaction proceeds. Okay, so these first three increase the rate of the reaction simply by having more collisions. They allow for more collisions. I don't like the way I said that. They allow for more collisions. And then even if only 20% of the collisions are effective, if you have more collisions, your 20% of a greater number is going to be greater effective collisions. Okay? The heat and increasing temperature, this actually works in two different ways. If you heat something up, the particles are going to move faster on average. So again, it is going to allow for more collisions. But since your average energy of each collision is now going to be greater, it also allows for more energetic collisions. So the first case is just, okay, if 20% of collisions will be effective and we have more collisions, 20% of a larger number is going to give you a larger number of effective collisions. However, combined with the fact that we already have more energetic collisions, more of those collisions is going to go from 20% to maybe 40% are now going to be effective collisions. Okay? Now, a catalyst actually works differently than these guys. A catalyst is going to work by lowering the activation energy on that reaction profile. And we lower the activation energy by rerouting what's called the mechanism. So by changing up the mechanism. Now, I know you don't know what a mechanism is yet, so just give me a second. Okay, so on one of your potential energy diagrams, your reaction profiles, just label, I'm just going to use this yellow, with a catalyst. Okay, so it's not going to change the potential energy of your reactants to your products, but it is going to change the size of this hump. Okay, and it's going to make it lower. I probably should have done that in a slightly different color. Maybe you'll be able to see this one a little bit better, or maybe not. But because that hump is lower, more of the collisions are going to have enough energy in order to have effective collisions. So if you go back to your effective collisions notes, we can now upgrade how specific we are here. Not only does an effective collision need to have sufficient energy, the energy of the collision must be greater than or equal to the activation energy of that reaction. And then don't forget, in addition to having enough energy with the collision, you also have to have proper orientation. Lastly, something you may not have ever thought of, what's actually going on kind of behind the scenes of a reaction. We see the reactants, we can see evidence that they've changed properties, the products are different, but what's actually happening? So we have kind of macroscopic observations we can make, but at that molecular level or at that submicroscopic level, what's actually going on is called a reaction mechanism. So it's the sequence of bond making and bond breaking that occurs to form the products at that molecular or particular level. Since we can't see that, a lot of this is educated guesses, indirect evidence. And one of the things we will strive to do in the kinetics unit is kind of put this together and meld the kind of what we see in the macroscopic world with what must be happening at the particular level. And that is called a reaction mechanism.